keep it simple, univariate polynomial as coefficients and degrees, coefficient, degree. List of all the coefficients, list of all the degrees. What's the size of that? The size of that is going to be the sum of the logs of the coefficients. That's assuming these are integers. If they're not, then if they have no size, it could just be 1. You know, if you count, I mean, it depends what that ground field is, and the log of the exponents. So I do have to, the exponents are all going to be integers here, and I do have to capture the length of the exponents. And so, what this often is it's the number of terms times the log of the degree times the log of the coefficient height. And that's really what the sort of the formula size, or at least some notion of formula size for a sparse polynomial is. And when we write something down with 5 terms, we want that size is going to be proportional to 5, or 5 times the log of the logs of the exponents, and not sort of proportional to the actual degree of the formula. So there's various words for this. Some people will call it a lacunary polynomial. Some people will call it a super sparse polynomial. Eric, if you're listening, I don't like it, but nonetheless. So lacunary, super sparse, and there's other notions. I think few nomials come up. I think few nomials tend to be polynomials with a constant number of coefficients. I mean, there's no really hard definitions of these things. But here's my representation of that polynomial there. So 1, and there's the degree, and so basically it's the coefficient and the degree sequences. So there's
no logs yet.
Pardon?
No logs yet.
No logs. I mean, no, but I mean, this is, as soon as I take the logs of those things, then but still, I mean, it fits on this slide, right? I mean, that's a very small.
The logs are built into the.
The logs are built in, yeah. And the point is that this is approximately as compact as that. So it's whereas if I wrote this out with all the zeros, then I'd have 2 to the power of 101 times 2 to the 99 zeros. I'd have a much larger slide. Okay, so now. There's other ways to capture sparsity and structure. I'll talk about black boxes, and so there's various other things. I won't talk about these now. So now let's look at the basic problems of computer algebra in this setting. So there's my polynomial f, factor f. Please. So there it is. That was easy.
Well, just you got lucky because the sparsity does mean that the factors are sparse.
Yeah, so this is a very contrived example.
Sure.
Let me say something about this. So first of all, it's a contrived example. Suppose I wrote down an example like that, and I asked you, tell me, does it factor? Is it irreducible? So there's an easy answer. Then I don't have this problem. There's a very important problem that the output size may explode. Turns out that's actually, for bivariate polynomials, is NP complete. So I'm in trouble almost immediately if I look at a polynomial like that, bivariate polynomial, and I ask you to tell me, is it irreducible? Not do this, which is cheating because I actually faked this, right? It's obviously, but is it irreducible? That's NP complete. So I'm in a dangerous zone already. So I want to be able to work with sparse polynomials, but I have a problem, at least in terms of the complexity. So let's just talk about complexity. Traditional algorithms, at this point, should be always run in time proportional to the degree. And fast algorithms run in times proportional to the representation size. And so that was my number of terms, the log of the degree, and the log of the height. So that's when I say fast for a sparse input or for a sparse output, that's what I mean. And so, I'll skip that. And these are these fundamental problems. There's this, actually this has been going on for a long time. There was some actually really beautiful results in the late 70s, early 80s. Plaisted showed that it's NP complete, and this is sort of the fundamental problem, is I give you a sparse polynomial and I ask, well, basically, does it have any nth roots of unity? Or, is it relatively prime with x to the n minus 1? Okay? Turns out that if I can do that, I can solve SAT. So that's NP complete. And then building on this and a few other techniques, Bivariate polynomials I just mentioned are intractable. Asking if there are any roots on the unit circle. Square freeness, so not even irreducibility, it's square freeness, that's intractable. I mean, so there's quite a range of ages there, 1977, 1999, there's still more recent things. And, but there's also a bunch of things, so at some level we could just throw up our hands and say, look, this is hard. But then there were a whole bunch of things that actually turned out to be easy. And so where we made a whole bunch of progress. So sparse interpolation is what I'm going to talk about here. It's actually been very, there's been a lot of success. I think the key result here is well, Grigoriev and Karpinski, and then this was sort of in a different setting, and then Garg and Eric Schost in 2009 sort of rediscovered it for polynomial interpolation. That's been taken towards polynomial interpolation with errors. I think one of the most incredible results is if I give you that sparse polynomial, that great big one, I told you it's NP complete to actually determine if it's irreducible, but if I ask, does it have any small degree factors, that turns out to be polynomial time, which I find, so this was a technique, so there's a sequence of techniques here which I just love. It was Cooker, Coran, and Smale in 1999 identified integer roots, and then Hendrik Lenstra said, well, for univariate polynomials, we can pull off small degree factors in time, polynomial in the size of the sparse polynomial and the degree of that small factor. That's an incredible result. It's also beautiful. I mean, I taught this in my 800 level, my grad algebra course. It's not that difficult. It's just brilliant. And this was taken to do multivariate polynomials by Pascal Coran and Eric Kalthofen. With my grad students, I looked at the problem of finding a sparse multiple. So I give you a dense, sort of the inverse problem. I give you a dense polynomial. Is it a factor of a sparse polynomial? So it sort of goes the other direction. Yes?
Can you go back one slide?
You can. I can.
So that in the GCD, the first component, can we assume that all the roots are length 1?
Or length 1.
Because isn't there an algorithm that says like you can measure the length of the roots, approximate the length of the roots?
Well, by length you mean what?
Modulo.
So the height.
How far it is from the norm.
Yeah. Well, I mean, you are looking for roots of height 1 here. You're asking whether are there any height roots on the unit circle is basically what's going on.
I'm saying that as far as like there's an algorithm to say whether or not it has any roots of length 1. And
but that problem is known to be intractable. So that's also it's a sort of subsequent result of Plaisted that its roots on the unit circle is known to be hard. So yeah, I sort of see what you're saying, but I have to see. I think there's a question of precisely what the question is. I mean, we can come back to it. There's been some recent work about this as well. So I mean, and one of the points is that there are easy problems and hard problems lurking right beside each other, and at some level the whole thing has a practical side. So it's important to get it right, and so coming up with the sort of the great questions is part of it. So I started in, and I mean this looks like self-aggrandizing, but it's not. I mean these are the really important results are at the top. But we did a whole bunch of things. I'll talk about a couple of them today. Perfect power detection. I might talk about interpolation. I'm going to run out of time, but this is new work, and so I may or may not get to it. Okay, so and there's a whole bunch of open problems. And there's work going on. I mean, actually one of these problems has possibly been solved recently. So let me talk about one just to get a flavor. This is Igor Sparlinsky in the year 2000 looked at the problem of detecting if f is a perfect square. So I give you the f here, and you tell me if it can be written as a square. So if determining if it's irreducible is NP complete, then we think, oh, it's possible that pretty much everything is NP complete. So it was kind of surprising at the time that actually determining whether this is a perfect square turned out to be easy. And so he showed how to do this, and he posed as an open problem to look at more general powers, and also proposed to look at something called sparse integers, which is basically the same thing, except where you had x to the I before, you would now have 2 to the I in an integer. So you have basically the location of the bits that are 1 would be a sparse integer. And so there's sort of an analogous world of sparse integers. And so we looked at this problem of I give you an input f, you determine whether or not it's a perfect square, so a perfect power for some degree. And so this has been looked at, this was sort of looked at for straight line programs by Eric Heltov, and it was looked at by Igor for squares. And that's me and my grad student. It was funny at the time, but he always beat me up. Anyway, so you have this, I give you the sparse input f, and I don't tell you r, and I ask you to find the r. All right, first of all, I have to ask you, does an h exist and an r exist, such that f is equal to h to the r? So and then the next step would be to find h if it exists, and this would require solving a conjecture of Erdős and Schinzel, which we didn't think we could do, which we knew we couldn't do, but nonetheless, actually somebody else did the hard work for us. And we also then, we would determine whether or not it exists. And we actually came up with a very fast algorithm. So it basically took time t log squared of the height and the square of the degree. The log of the degree squared. So this conforms to my notion of fast, right? It's fast. Okay, so how do we do it? The algorithm's kind of weird. So first of all, there's my input. I have an integer polynomial f, and I'm going to just start out with a prime r. I'm going to give you the prime r. And I ask, does there exist an h such that f is equal to hdr? And I'm not going to attempt to compute h precisely because of what you said, that h may actually, in principle, be huge. So you could actually have that a sparse f is the 5th power of a dense h. Now, nobody believes that's true. But up until 5 years ago, we had no proof of anything. Now there's some recent work of Zanier, who has shown that it may be that there is some hope for this. And this is this conjecture of Erdős from the 1950s, or as a version of a conjecture of Erdős. But here's the algorithm that actually just detects if the h exists. You choose a random prime p, which is pretty small, and such that the r that we're trying to find divides p minus 1. And we choose 5 numbers in ZP. 5. 5 is important. I mean, that's not really, but a 5 works well because it makes the probabilities work out. And then we compute this funny thing. We take our polynomial, we evaluate it at that alpha I, and we raise it to the power of p minus 1 over r. Now, some people, if you know some number theory that looks like a Legendre symbol or something like that, it actually is a, except that you're evaluating a polynomial. Well, I can't even evaluate an integer polynomial at a point because it has really high degrees. So if I evaluate that f at 2, of course I'm taking 2 and I'm raising it to the power of whatever degree that polynomial has, and that's immediately, I've lost the game. I'm immediately into exponential complexity. So I can't even do that, but I can evaluate it mod this small prime. Because the small prime means everything keeps wrapping around and everything stays small. So I can actually do this. I'm doing all these evaluations mod p, and then I'm computing p minus 1 over each of those to the power of p minus 1 over r. And I can compute high powers of things by repeated squaring. So these big exponents actually don't hurt me at all. And so I get 5 numbers in ZP. If they're all equal, I say it's an rth power. And if they're not, it's not. And that's my algorithm. And that algorithm works. And so why? Well, the reasons are not that surprising. The proof is more difficult. So if this psi is in ZP is an rth power, if and only if when I raise it to the power of p minus 1 over r is equal to 1. So that's sort of a condition on, it's a sort of an algebraic way of detecting whether something is an rth power. Now you have another thing that says if f is not an rth power, then f mod p probably isn't. What do I mean by that? Well, for a randomly chosen small prime, this holds. There are a few bad primes where the prime divides the discriminant where things can get bad, but that's a very small number of bad primes. The next thing you say, if f is non-equivalent to h to the r mod p, then f of psi probably is not an rth power. Okay, this is the hard part of the whole exercise. Because this involves the last thing, which is his last ingredient, which is there's this beautiful theorem of Von Drake on character sums with polynomial arguments. You turn this probability here into a character sum argument, and you show that the number of bad points, the bad selections, for randomly selected, for a random p and random alphas is small. And now small means small enough that if I do it 5 times, I've raised the probability of success to greater than a half. And so the magic, in a sense, or the big hammer is Bayes' theorem, and the magic is to be able to translate this very simple algorithm into using Bayes' theorem. Okay, and I'm not going to go into details. I mean, it's maybe sort of a 3/4 page character sum proof. I mean, and somebody who does character sums would actually see it as relatively standard.
Is there any reason to pick 5?
5 is enough of a probability to make the probability of success bigger than a half.
Oh.
And once you have it bigger than a half, you just keep on cranking, you sort of ramp it up until you can make it as high as you want. I mean, I could have said 2, but it would sound less magical. I mean, the truth is that it just has to be, you have to choose enough so that you get this consistency, and then you show that, well, if they're all equal, then the probability is bigger than half. So there's nothing really special about 5 here. Evaluation, so let's give an example. What time am I supposed to finish?
What time is your flight? Okay, you have at least 10 more minutes.
10 more minutes, okay. I mean, this can go on.
Sure.
This is the second talk. So here's the example. This is for cubes. We take our polynomial, we choose a prime p is 37. We evaluate each of these, and each of them is going to be 1, which says it's a perfect cube, and indeed it's a perfect cube because I cheated, and that's why that's grayed out, because you don't know that thing over there, you just know that polynomial there. And actually going from that to that is quite difficult, right? Because I mean the actual, and I'll talk about that in a second. Okay, so now if I add a 2 here instead of a 1, I've created something that's not a perfect cube, and it's not a perfect cube. And if you look at now when I compute these things, of course, I don't see that they're all equal. I see that they're quite special values, but they're not the special values that matter. And of course, they're not all the same. Therefore, I say this is not a perfect cube, and that's right most of the time. Now, that's sort of a complexity theorist kind of problem, right? It really is not that, it's not that often you want to know something is not a perfect cube. It's much more likely you want to compute H. And the problem is that H may not be sparse. This is this conjecture of Erdős in 1947. He says, if I say tau of H is the number of terms in H, Erdős conjectured that if f was h squared, then tau of h had to be less than tau of f. Okay? I mean, it actually probably should be the square root of the number of terms is sort of what you expect if you look at the number of constraints and things like that. But it really is, that was his conjecture. It actually stayed open until 2008, and it's still, I mean, it's closed in a sense that Zanier showed in 2008 that tau of h is a computable function of tau of f. So that means the number of terms in H is a computable function in terms of the number of terms in f. Why does this solve it? It solves this because the thing you don't see mentioned there, the thing that you don't see mentioned there is the degree. There's absolutely no mention of the degree. This is completely independent of the degree. And so this was an incredible breakthrough. So I mean, mathematically, in some sense, this actually solves Erdos conjecture. And Janier has gone on and done a whole bunch of other very impressive things along this same line. So, so what do? Well, we don't solve Erdos conjecture. We don't solve, we don't try to refine Zanier's conjecture. What do we say is we basically go with the standard hypothesis that, in fact, that if f is sparse and h exists, then everybody believes that h is sparse. So what are we going to do as computer scientists? We're going to say, well, let's just assume h is sparse. We're going to make the complexity in terms of the size of the input plus the size of the output. And so when the mathematicians get around to proving this, or when they don't, I mean, our algorithm will still work, and it will work with whatever, it's sensitive to whatever the actual bound is. So what we came up with was an actual algorithm to compute h. So this is actually after the first one, we said, okay, we want to compute h. Let's come up with an algorithm, and we actually came up with an algorithm that does it in time. And the O of 1 here, so I went to Massus in 2000, no, Dan went, because it was his first talk in Massus in 2000, I said 10, maybe it was, I mean the conference was 2009. I think the exponent we had there was 78. That's a fast algorithm. It's polynomial time with an exponent of 78. And the reason is that Linux constant actually comes, the exponent in Linux theorem comes in there in an ugly way because we need to find primes with certain properties, or we did. Now we've got it down to somewhere around 7 or 8, but it's a fairly brutal, it was a fairly brutal.
Randomized algorithm?
I think you can actually do this without randomization at this stage. I mean, as long as you assume that you have a bound on the output, I don't think there's any. I don't think you need randomization at this stage. The randomization, which made no assumptions about this, about h, was randomized. You know, the one where I selected. This is actually a deterministic algorithm, is my recollection.
Because the output is h.
The output is h. It's certainly Las Vegas, yes.
Yeah.
Well, okay, so that's actually an interesting question. So if I give you f, and I give you h, and I give you r, prove to me that f is equal to h to the r. Now I know that we can do that, but this took us a
around
long...
the same modulo prime.
Yeah, but you can have, how do you throw away the bad primes? So the only way we could actually figure out to do this is using logarithmic derivatives, and the only way we could figure out was to use logarithmic derivatives is that Pascal Coiran told Eric Schost, who told us that we could use logarithmic derivatives. They said, you should try logarithmic derivatives. And so there was this chain of sort of comments on our paper that came back to us. And so we immediately went away and tried logarithmic derivatives. And sure enough, if you take the logarithmic derivative of both sides, then it's pretty easy to actually do it. And it's a very, very cute result. So anyway, it's actually not trivial. And the reason that Pascal Coiran knows it is there's actually he's a complexity theorist, and there's a very interesting problem in complexity which is not known to be solvable, which is close to this. Now, I'm running out of time, so I won't talk about this. I'll talk about so there was actually a motivation for this problem, which I can't remember. But one of the things I wanted to point out was that, so these are theoretical algorithms, but we did implement them. And the reason we did is because they don't just work on these extreme cases, on these extreme cases where the degrees are 2 to the 100 or 2 to the 200. They work actually well at very low degrees. So this is the dense algorithm. This is just sort of doing it, as fast as we could possibly implement it, computing an h, the rth root, basically given f, find h such that h to the r is equal to f. And then we use the sparse algorithm, and you'll notice, and so these are, it's not, the costs are vary quite a bit because various cancellations occur quite regularly. But I mean, you notice that this is there's a lot of stuff in this is time going up this axis. This is a much more expensive algorithm. This in the dense one. You know, even at small degrees, look how much better these sparse algorithms are working. And that's sort of the thing we're trying to do is for this whole slew of problems we've now attacked here is that, yeah, sure, we're attacking them at a complexity theoretic end, but we're also really trying to implement them and show that they actually run quickly in practice. And the remarkable things is that the things that we do to make them polynomial time in the log of the degree also have a very good effect in terms of the complexity. Honestly, I'm not sure I think it might be biased just to call it do you want me to talk for 10 more minutes, or do you want me to?
No, I'm fine.
Yes,
I mean, okay. So I wanted to talk a little bit about sparse interpolation. And because I think sparse interpolation is cool, and I'm sorry for the people who sat there were 3 or 4 of us who sat around where I explained the gist of this talk. Anyway, this is my Prani paper, but I want to show you what Prani did because I think it's a fabulous result, and it's sort of, I think it's where the success of sparse algorithms in computer algebra has been, and there's some work I want to point to that's ongoing. So what he actually looked at is if you have a function which is an unknown sum of a small number of sparse exponentials. A small number of exponentials. So there's a collection of t where t is small. T is 5, something like that. And there's a delta j, which is the exponent, which in his case is a real number, or even a complex number. And the fi, which is an unknown coefficient.
Is supposed to be delta I also?
It should be delta I, sorry, that's a delta I. Yeah, fi and delta I, yeah, sorry about that. Okay, and then you evaluate this. And he said, well, evaluate at f of 1, f of 2, f of 3. The point being at very regular sums. Could we reconstruct f with a small number of evaluations? That was his problem in 1795. And this is what I was saying. So what he regarded is that he was seeing I mentioned that these delta i's were sort of the structure of the problem, and the coefficients were the magnitude of the problem, the measurement of the problem. And the difference from sort of the interpolation algorithms of, I guess, Legendre, 20 years before, was that he noticed that we really needed to capture structure as well. Okay, now skip forward to 1980, and there was what's regarded as a breakthrough result in computer algebra / complexity, whatever, which was Ben-Or-Tawari, and Michael Ben-Or and Prasoon Tawari, and they determined so you have a polynomial now, f, such that I can evaluate this polynomial in a black box. We don't know the polynomial. You put in some point, and you get out f at that point, and the point you put in is omega to the power of I. And where this is a when I say to the power of I for a multivariable vector means that raise each coefficient to the ith power, each entry. So if it's 2, 3, then you do 2 squared, 3 squared, 2 cubed, 3 cubed, 2 to the 4th, 3 to the 4th, and you look at these powers of this omega. And what he showed is that if you have t terms in your sparse polynomial, then you have to look at 2t minus 1 powers of the point. You look at the evaluation of those 2t powers of the point, and you could reconstruct the original polynomial from that. So that, I didn't say here, the number of points that Prani needed was 2t minus 1 in 1795. The number that they needed in 1980 was 2t minus 1. And so start to see similarities. And exponential interpolation and multivariate polynomial interpolation are fairly similar. And the difference is that, 1980, and especially in 2015, we have an incredible motivation to represent polynomials in a sparse way, or to represent polynomials in the best way we can. And there's all kinds of motivations for interpolation that I won't go into here. But I think it's easy to say it's one of the most fundamental problems in computational math. So here's some pictures. And so this is Eric and Wenshin Lee, who I think had the, in Wenshin's thesis in 2003, they started working on something where you would even learn you didn't even need to know T, so they could identify the sparsity as they were going along. And that was in her thesis. She came to Waterloo as a postdoc in 2002 to 2005, and we started to look at well, this was actually when she was in North Carolina doing sparse shifts, but we started to look, when she came to Waterloo, we were just starting to look at numeric algorithms. And so we started to look at numeric sparse interpolation. So the idea here is that we have a sparse polynomial, and we throw in we have noise. So the point is that when the coefficients become floating point, we end up with issues of noise in our sample points. And in particular, if this is about sampling a function that actually has noise as well as sort of truncation from floating point computation, it actually becomes a much more interesting problem numerically. And so there's a lot of reasons why we would do this. So I mean, homotopy methods is one where people have actually used some of the techniques that we've been working with. So one of the things that I like about this, so I'm not actually going to go, I think I will skip over the techniques there from this, it'll just be a pointer, is that this work is, this is Wenshin now, she's now in Belgium, and in Antwerp with Annie Coint, and so they've been looking at sparse interpolation there. And the reason that they care about sparse interpolation is that rather than polynomials, they're now looking at signals. And polynomial interpolation and signal processing are also very closely related. And the reason why you might want to do it sparsely is because actually measuring the signal has a very high cost. What's the cost? Well, there's a cost in terms of power and there's a cost in terms of processing. And so the temptation is to say, who cares? But they're looking at heart monitors and EKGs or EEGs, and the reason they care is they want you to be able to wear them around. And so they want to identify problems with a heart condition, whether it's and they want to be able to do it on the fly, and they want you to be able to move through the world. And yet, when some arrhythmia starts up, they want to have it detected. And you can't be walking around with your, even a reasonably powered PC on, you want something very lightweight and something very low power and something that has very high battery life. And so sparse interpolation is exactly what you need. Now it's a sparse interpolation of the EEG signals where you're looking for particular kinds of shapes and anomalies. And so they've taken that in this direction since then. Okay. Prani's method is actually quite magical. And I think I'll just say it just to point out the magic. You start out by choosing a sample point, omega, and you evaluate at the powers of that sample point. And now two marvelous things happen. First of all, at t terms in, the t plus first term becomes linearly dependent on the previous t. And the t plus second term is linear dependent on the previous t. The t plus third, so basically there's a t term linear dependence of the next coefficient. So even though we're evaluating a highly nonlinear polynomial here, there's a linear recurrence in these evaluations. So, I mean, that's not hard to work out, but it's kind of cool. So then you say, okay, well now I have this, I can solve for it. So I put this into a matrix, and this is nice, it turns out to be a Hankel matrix here, where I basically solve for these coefficients. I say that f of omega to the t is some linear combination of the previous ones, and this is f of omega to omega to the f of omega to the t here, and it's the same linear combination, etc. So I can solve for this using linear algebra or fast linear algebra or the Berlekamp-Massey algorithm. There's a whole bunch of ways of doing this. And then I turn that into a polynomial. Say, okay, well, Mark, why would you turn that into a polynomial? Or Baron de Prani, why would you turn it into a polynomial? Because then you can find the roots of that polynomial, and the roots of that polynomial turn out to be precisely the powers of the initial point you chose, and the powers that you find are exactly the exponents in your polynomial. And that's actually pretty magic, right? Because what that means is that by now doing essentially a discrete log here, you can now pull out the structure. And once you have the structure, you're done. You're done, at least in a computer algebra sense. You can just, linear algebra will buy you the answer. Well, you can compute the answer almost immediately. Okay, so it's a wonderful algorithm. And that's the basis for Prani's algorithm. It's the basis for Ben-Ortuari's algorithm, these two observations. But now you have a problem. Now we throw in a polynomial, which we'll say is a complex polynomial. We have we have noise in here. We're using floating point numbers. Everything's much messier. We can still solve this problem, but this matrix now may be numerically horribly conditioned. And this discrete log problem may end up with the wrong answers, and the linear algebra here may be unstable. So all kinds of hell breaks loose in solving this problem numerically. And in fact, so much so that the numerical analysts abandoned this algorithm to a large extent in the 50s and 60s. And it really was because the Hankel matrix is ill-conditioned, the root finding is ill-conditioned. It's just generally bad. And so what we came at this from a very naive angle, as computer algebra is. Well, George is not. So first of all, George Le Bon looked at this, and Wenchen came in, and Wenchen and Eric and I had been working on this. And George says, I know that. That's Prani's algorithm. He's a numerical analyst. He said, that's a stupid algorithm. He didn't quite say that. But then we said, yeah, but look, we're randomizing this. And then we said, okay, well, we don't have to choose a particular point here. We can choose any point. And by the way, let's choose a point on the unit circle, and let's choose a random point on the unit circle. And we're going to use that as the basis for Prani's algorithm. And suddenly everything got interesting, because as soon as you do that, you immediately make this matrix here, at least in practice, much, much better behaved. So this matrix here becomes much better conditioned. The condition number in practice goes dramatically down. The root finding here gets dramatically better. And therefore, the discrete log and this last linear algebra step gets better. So suddenly all the matrices in practice become very well conditioned with high probability. At least that's the observed thing. And now, so then we start grinding at the proofs, and we prove A bound, which I won't show you here. I showed Victor and people earlier, which is sort of satisfactory. And it's sort of satisfactory, and it says that the condition number is only dependent on t, the number of terms, and not the degree. That's good. So it sort of says sparsity. This is a sparse algorithm, and the dependency is only on the number of terms. Unfortunately, it's exponential in t. So at least the best we could prove is it's exponential in t. So that says to me that, okay, so for a constant size support, so for a constant number of terms, this is a good algorithm. In practice, it's a good algorithm all the time. The proving it's a good algorithm all the time seems to be a very difficult problem. So we've actually then gone back to one of my first loves, which is character sums, turned it into a character sum in an analytic number theory problem, and been talking to Igor Sparlinsky, who remember from a few slides back, who has some ideas about how to make this work as a character sum problem. But I mean, it's a very difficult problem, and it actually touches on some very well-known problems in analytic number theory, which are well-known because they're well-known to be hard. So that's not necessarily a good thing. Nonetheless, I think I'll stop there, and I'll start with a bit of a statement, a mission statement here. Sparse representations really matter. We need to be able to compute quickly with sparse and structured mathematical objects, and we also have to know what to avoid. So we have to be able to avoid those NP-complete problems. We have to know what the right questions are. So, I mean, the best example of this I can think of is the Lenstra / Kalthoff and Coram low-degree factor algorithm. I think that's brilliant. The original problem was NP complete, appeared to be hard in practice, and yet if you just say I'm interested in low-degree factors, suddenly you have a very nice polynomial time algorithm that actually works well in practice. I think that's sort of the right mindset for these things. So you want to identify sparsity when you can, extract the sparsity, and you want to do it with a small number of probes or the smallest number of operations possible. In terms of numerics, you want algorithms which are both provably stable, and if you can't get that, at least get algorithms which are numerically robust in practice. And so, approximate algorithms, robust solutions, and I think there's a competing technology out there, certainly in the signal processing world, which is compressed sensing. I think we can both attempt to compete, but I think we can also hybridize. We can make use of compressed sensing in the middle of some of these algorithms, which is something we've started to do. And real-world problems and data sets, this is definitely what Wensch and Lee and Ernie Coit are doing these days. So with that, I think I'll finish it up. So thank you very much.
More questions? Let's move to the party then.
Oh, yeah. Okay.
With whatever questions you have.
Now you can ask me questions later.
Come on.
Great talk.
Yeah, it's fun stuff. Yeah, 2 times Saturday, but man, you guys work super hard.
Mine is with.
Yeah.